Good morning, everyone. I appreciate you joining us. If you're joining us live, I just wanted to point out that I'll be turning this over to Dr. David Bourne shortly, and he will give his presentation. If you have any questions, you can type those in chat, and we will address those most likely at the end of the presentation. If you are watching this as a recorded video, then you can reach out to one of us, through the website, and we'd be happy to provide answers to you. So, okay. So I am going to talk just a little bit about, for those of you who maybe are not as familiar with the AIM Hire Consortium, and that's who is hosting this and bringing you the content. So just going to give you a little bit of information about AIM Hire, and then I will turn it over to today's speaker. So the AIM Hire Consortium was funded by the Department of Defense. The OLDCC provided funding. We are, as you look on the map there, you can see the entire state of West Virginia, as well as the 12 counties of southwestern Pennsylvania are the footprint of this program, and the focus is on the adoption of advanced manufacturing technologies and helping small and medium-sized manufacturers in these counties to make connections within the Department of Defense supply chain. And that could be, at any tier level. It could be first tier level, which are usually large corporations, but it could be second, third, fourth tier, providing parts that ultimately go to support the Department of Defense. So we do a lot of different activities and helping companies. Let's see, let me go to the next slide. You can see here are all of the partners that are part of the consortium. My name is, I should have said it right off the bat, my name is Tom Reed. I support the communications efforts with AIM Hire, and you can see all of our other partners, Innovation Works, CTC, and you can see we have economic and workforce development partners. We have technology institutes, which are national institutes, and then we have some of the leading universities in our region are also all in support of the AIM Hire Consortium. And we work together to provide a variety of services and education and support as we go forward. If you visit our AIM Hire Consortium.org, you can, not only will you see other AIM2Learn videos like this one that cover topics, but we have a lot of other information, and one of the newest ones that we have launched on the website is called the Supplier Capabilities Database. So any manufacturer or any supporting organization can go on and enter their own listing into this database, put information about your company, your capabilities, what it is that your manufacturing company, how you could fit into the supply chain opportunities, and then and once you're on there, we are promoting this to supply chain managers and clients who would be looking for those capabilities. So someone can go in and sort and search on specific capabilities, specific certifications. So again, it's just another way for small and medium-sized manufacturers to promote themselves and get themselves in front of those who are looking for their capabilities to support the Department of Defense. All right, so with that in mind, I want to, let me just back up here. I would like to welcome today's speaker, Dr. David Bourne. Dr. Bourne is the Principal Scientist of Robotics and the Associate Director of the Manufacturing Futures Institute, both with Carnegie Mellon University. So welcome, Dr. Bourne, and thank you for your time.
So good morning. My name is David Bourne. I'm a Principal Scientist at the Robotics Institute. We've just started this new institute called the Manufacturing Futures Institute, and its focus is on manufacturing, And one of the big questions that everyone's asking is, why is it cool? Why are we doing, how is this different than robotics? What's different about the Manufacturing Futures Institute? So the simple answer here is that it's all about digital twins, and you may or may not know what that is. So that's the reason for this discussion today. I've been doing manufacturing research, especially in robotics applications, since 1979. So I have a little bit of experience, and now I'm excited to actually see lots of new energy being put into the manufacturing domain. It's really been my whole professional career, and I'm excited to share with you some of my insights and what I'm thinking that the Manufacturing Futures Institute has in mind for us all. So what is the manufacturing future? Is it about robots? Is it about artificial intelligence? Is it the cloud? Is it the Internet of Things? Is it machine learning? And I think the answer is yes, it's all of these things, but really this is not what's unique about the Manufacturing Futures Institute. It's all about the ubiquitous digital twin. And that's what we're going to talk about and explain to you what that vision is, so that we can go ahead kind of with a shared vision and really an understanding of what we're all trying to accomplish. Let me just say here at the beginning that this is somewhat aspirational. This is new. We don't have, if you go to the MFI at Mill 19, this is not all in place yet. This is really the vision for the future. But we do have a clear vision. We do think it's going to be amazing and cool and offer new solutions in the manufacturing space that we really could only have imagined up until this point. So what is the digital twin? And you can go out and Google this and find probably different definitions, but I think you'll find that most of them have much of this in common. So a digital twin in simple terms is a computer representation. We've had data structures and representations of the real world, fancy graphic simulations of the real world for a long time. For really the last 40 years, we've had pretty good factory simulations. But what's different about this? What is really different? So the idea here is to have this model that's synchronized, that's in step with, in real time, with the real world. So basically, at any moment, we know that our model is basically reflecting exactly what's in the real world. So it's not some just graphic simulation that you can pull up and run and basically say, oh, here's our factory, but it's totally, it's doing something totally different than what the real world is. This is like a real live stream with the three-dimensional models being updated. Now, having said that, it doesn't actually have to be graphic. So that's one misconception right off the bat, that everyone gets very easily to the point that what's going on is kind of a three-dimensional graphical representation, like a computer game, in the computer. Now, that's in fact part of it. Maybe it's all of it. Maybe it's not there at all. The representation in no way insists on it being kind of this 3D graphics representation. It does need, so I'm going to start telling you what the characteristics are. So actually, I find this a very interesting way to think about how to define something like a digital twin, or for that matter, Industry 4.0. So if you're up on what Industry 4.0, you may say, oh, this is a big overlap with that. And that's true. That is true. There is the technology I'm talking about today actually is included to some extent in Industry 4.0. Now, Industry 4.0 is much more elaborate, much more inclusive than digital twin, but digital twin is also a more foundational technology. So in a way, it's more ubiquitous, more all-encompassing than Industry 4.0, because Industry 4.0 has very specific applications in mind, where the digital twin is really could be applied to anything. It's not limited to manufacturing at all, but it's going to have an amazing impact on manufacturing. So the first characteristic really is it needs to have the fidelity appropriate for crucial problems. And what that means is simply that there needs to be enough resolution, enough detail, so that when you're going to solve problems, that the details are actually captured in the digital twin on the computer side. It needs to be easy to synchronize to the underlying physical phenomena. So if you're trying to model something, being able to capture what's going on in the real world and reflect that in the computer needs to be relatively easy. This can't be something that's complicated, or you have to run special programs. This is an ongoing, continuous thing. It's basically alive. It's matching what's going on in the mind of the computer. I'm loosely speaking. What's going on in the computer is always reflecting what's going on in the real world. Now, having said that, just this simple kind of video stream doesn't really allow you to do much, right? It's like turning a video recorder on and having it capture something, but you can't really reason about it. So there needs to be the ability to simulate various paths forward, so that while you're recording, you need to be able to think about, the computer needs to think about what you're watching. So part of that is to understand what the next state is. So does the computer, so one of the goals here is to basically change the world according to a computer plan. In other words, we want to, for example, we want to make a part. So how do we get the real world to make a part? What if the real world doesn't go right? There's a machine tool breaks, something like that. So there needs to be, while this streaming is going on, capturing the continuous state, we need to basically be able to plan alternatively other paths forward. Eventually, we may want to say, okay, let's try and execute this and make the real world actually match what we're thinking in one of these possible streams. So I'm suggesting there's multiple streams. There's the one that's actually going on, capturing the real world, but then there's hypothetical ones as well. There needs to be evaluation metrics. So, none of this is any good if you can't make it come to some conclusion. So, for example, if we're thinking about moving the robot, is there any collision checking? That would be bad. So we want to avoid that. So collision checking needs to be part of a planning process, so that basically you'd move a robot so that there was no collision. There may be other criteria, metrics, meaning various, rateable criteria for one plan over another. So is this a more desirable plan than another one we've tried? So desirability here would be simply, it's faster. That's the most obvious one. This path is faster than another path. It needs to be safe. Is there any dangerous activity going on? So there could be a whole range of these carry forward predictions about the real world state. So we're capturing the continuous stream, and then we're considering all these possibilities, and eventually we can switch over from one to the next. Now, this is not really going to be just for the computer, kind of in the mind of the computer with no window into it. So we'd like to be able to visualize the twin. So if it is graphics, we'd like to see the three-dimensional graphics of what's going on. Or we'd like to see the three-dimensional graphics of a possible plan forward. So visualization, I think, is really a critical characteristic. It's not a necessary characteristic because people aren't necessarily part of this, but I think really the usefulness of a digital twin, being able to visualize it, is really essential. Now, having said that, I think there needs to be a well-defined interface to higher level systems, software systems like planners or schedulers or designers, but also even software interfaces to, again, access or find the state of this so that you could ask questions. So it'd be great if you could basically walk into the building and say, which machines are running at the moment making parts? And it would come back and tell you that the 5-axis machine number 3 is currently in operation. So being able to interact with it in an intelligent way, kind of like Google Assistant. So this enables, let's say, a Google Assistant for manufacturing, where you can ask it questions that are related. So I think this is a key characteristic, and if you Google this, again, you won't find this as a particular necessary condition because people may not be involved in it. But again, I think this is what really makes it a powerful new technology that we really don't see. So I really do envision walking into the manufacturing facility and being able to ask questions and direct actions. The building itself should be part of this digital twin, in my opinion. So you can say which conference rooms are being used, or are there any new are there any trucks loading at the loading dock? So the digital twin should know what's going on about the state of its entire space. But it's not, the digital twin could be very narrow and just talk about one machine, or it could be as broad as basically the whole facility. The key to the digital twin is this mapping between the software representation. You see these two big Venn diagram like circles on the left here, the digital twin, which is in the computer, modeling what's going on, and then the real world. And then being able to synchronize it. And I show the synchronization going both ways. that may seem a little confusing because normally you'd think the digital twin was matching the real world, which is the bottom synchronized going real world, changing the state of the digital twin. But if we go ahead and plan something, plan future actions, we'd like to synchronize the real world to match the digital twin. So you have kind of an option whether you want to update the digital twin to match the real world, or do you want to update the real world to match the digital twin? Now, this is the key point. This is what makes it exciting to be able to go either way. Just one way is kind of boring, frankly. But if you can really go both ways in kind of an intelligent format, I think this should start to become clear that this is something new, this is something powerful, this is something futuristic. I've done part of my past is to think about computer programs and understanding natural language and thinking about what meaning is. So the word meaning. In a sense, the mapping between the digital twin and the real world is what gives the digital twin real meaning. It's three-dimensional objects kind of floating around or doing a computer game, in some sense, don't mean that much. But if you can really show how they and know about this connection to another domain, that gives meaning. So it's like words. I'm saying words now, but they refer to semantics, all shared common knowledge that we have. Well, the shared common knowledge here in this case is the real world state. And so this mapping between one and the other is really what gives this whole idea of digital twin meaning and what's so exciting about it. So on the pictures below the digital twin, we have really a nice high fidelity graphics simulation that I did in one of my projects that shows a robot arranging parts that are going to be welded in a manufacturing setting. This is a real robot, a real welding station at a fairly high fidelity. Now on the right side, there's actually an image of the real world, and it's basically being highlighted with laser. So there's kind of blue and green crazy stuff there. Those are projections, laser projections, to highlight where a person would need to move a part. So the part's above the blue area, and the purpose of it is to have a person move the part into the blue area, updating the state. So this is when the real world is updated, it could be the robot changing the state of the real world or a person changing the state of the real world. So there's no requirement that this be the next state function, the ability to go from one state to the next, be all digital. It could be actually commanding a person to move from one step to the other. People are very good at changing state, or changing state of the real world. So we very much intend to use that. Digital twins are not does not specify that everything needs to be computerized. That in fact, we're especially interested in the interaction and interrelationship with people in this world. And so we want to include in kind of a logical way to include the actions of people. So there are two kind of forms of digital twins, and I want to call them passive. And I think that's what probably people would normally think about in the first place. In this case, we're basically monitoring what's going on in the real world and capturing video, maybe capturing sound, capturing signals from manufacturing processes, and just watching them, monitoring them, maybe looking for a particular state. So we might ask questions like, what is the temperature outside or inside the building? And let me know when the temperature is over 90 degrees, in case something's going to overheat or something like that. So we can monitor something in this passive state, but in a passive state, it really doesn't allow us to do anything to affect the state. That's why I call out this second idea, which is an active digital twin, which is one that can branch off into various possible worlds and cause the world to synchronize to the digital twin. So that means we're going to plan something for how to make a part, let's say. We're going to have kind of a hypothetical universe that's got that plan worked out. And then we're going to go step by step and ask a person to participate in bringing that to fruition, or robot. Or it doesn't have to be a person, but it certainly could be. So this enables a range of applications like planning compute actions to bring a world to a given state. So manufacturing, again, what are the operations to make a given part? One of the things I've spent a lot of time working on is when things don't go right. So you have robots and machine tools, cutters break, robots drop apart, various things like that. If it can happen, it will happen. So there's all kinds of errors that often bring automated systems to a stop. And so this idea of digital twin gives us a chance to find the state, because we're monitoring everything kind of in an area, and come up with a plan to bring it back into normal working conditions. Usually when manufacturing steps in robots fail, it's kind of trivial. On the other hand, the robot's not looking for it, so it doesn't really know what to do. So error recovery is kind of an essential element in order to keep to maximize uptime of an expensive facility. And teaching, tutorials for getting people to understand how to make things and how to run the system. So here's just a couple of examples. So there's two different kinds of milling. There's actually a lot more, but the two basic kinds of milling, which determine which have to do with the direction of the feed and the direction of the tool relative to each other. And there's very strong reasons to pick climb milling over conventional milling. So in the case of climb milling, the direction of the tool is basically counterclockwise in this picture here, and matches the direction, the effective direction of the feed. The feed is how the part is being moved relative to the tool. So it turns out that climb milling is much more efficient. You can run the tools faster, so you can cut faster, and there's in some cases less tool wear. It's actually much better, but industry has kind of shied away from it because there are issues with backlash, and there's a backlash is the situation where the robot's axes are, or the machine tool, a cutter, CNC milling machine, basically absorbs the motion, and you know it's not perfectly rigid, so it can move a tiny bit this way or that way, and climb milling tends to push the machine to one side of that kind of little wiggle room that every mechanical machine has. And so basically backlash is a problem, and which means it's hard to hold tolerances. And there's some other issues with hardened materials and things like that cause climb milling. So that's why industry for the most part goes to conventional milling, even though it's much less efficient. So now that we understand the basics of that, we can start to look at the signal of what's going on and try and use climb milling unless there are critical signals that start to show up. And so here's a vibration signal that's set up on a milling machine, and you can actually, if you look at these enough, you can start to read them. They look like, kind of like English. Not really, but they start to tell you what the characteristics are. If you're an expert at it, you can just glance at this and basically decide whether there's unnecessary chatter, there's unnecessary backlash, whether the climb milling's not working, whether you should switch over, because you're doing this monitoring. And so this is a case where the monitoring is not necessarily visual, keeping a three-dimensional model up to date, but really monitoring the process parameters that are critical to milling. Now, you probably want this going on in conjunction with the visual graphical part of this. So this would just be another dimension of the digital twin. Now, planning, in this case, we have a bending machine and planning how to set it up for a given part. And so in this case, we have a bunch of parts we want to make, and a planner would go out and figure out what the tool layout is, in this case, punches and dies on a bending machine, and where they should be located so that you can effectively bend a three-dimensional part, coming up with an optimal plan for that. Now, to accomplish that, we basically break off, we split the stream and come up with this hypothetical plan. We come up with basically a series of steps to load these new tools on, and then ask an operator to go ahead and do that. In some cases, you can automate this, but in this case, we show a person being directed to load the tools. Now, in the system I built personally, I use the back gauge to basically guide the person to where exactly to set up the punches and dies. So he doesn't even have to measure it. Basically, the machine is cooperating with him on kind of a step-by-step basis. And on the instructional side, if we have a three-dimensional graphics and we're kind of thinking, the digital twin is thinking ahead of what to do, it can basically show a person a simulation of what's expected. And so in this case, it basically is asking a person to move you see a part in the top part, it's blue, light blue, and the system's asking it to move that blue part into the green area. So it gives a very specific directions. So the person doesn't have to wonder whether the part's this way or that way, or whether the part should be put on the other. Doesn't have to look at blueprints. He can basically see exactly where it goes. And so this is an application for augmented reality as well, where you can kind of combine what the digital twin is thinking to basically give a person direct access to that thinking and help him carry out these next step functions. Now, once you do that, you get to this situation that's I would say amusing from my point of view, but it also throws a lot of people off. I've certainly heard people over and over again say, well, the robot just does what a person says, right? And my answer is, no, that's not right. Actually, if a robot knows what it's doing and it's going to work with a person, more often than not, the robot's going to be the boss telling the person what to do. Now we see kind of why that might be, right? The person doesn't know all the details of a complex assembly, complex operations to make a part. Actually, a robot's really good at keeping track of all that. So the robot can basically step a person through a very complicated process, getting the person to do it. Well, if you can get a person to do it, why not have the robot do it all? That would be a question you could ask. Well, that's true, but do we really want to put robots dangling from the ceiling? And do we want thousands and that? They're expensive, and they don't always work. So having some people there makes a lot of sense. And so we do want people to do kind of let's say the miscellaneous work, or the work the robot can't do. And so we want a person to do those functions. But having said that, again, the robot knows what it needs, and so can give the person direct directions, direct tutorial information of what it expects to do next. So from a theoretical point of view, then the question comes up with who actually has the initiative here. Is it the human or is it the robot? And it turns out that there's a lot of cases in manufacturing where it's really helpful to have a robot and a person working hand in hand, and to switch the initiative. So the robot sometimes is doing the next step. We talked about that. And sometimes having the person do the next step, and to basically trade that initiative off, depending on who has the best information for a given task. So if a person can see a hole and the robot's not in a position to see a hole, and you need to put a bolt through it, then the person can basically give advice or direct the robot to do that. So in this kind of shared initiative state, like if you were working with a friend to do a complicated assembly and you can't see something, but your friend can, and so you want to be able to trade off on that initiative. So I just want to remind us that a digital twin is not limited to a graphics representation of a basic step. It can really cover all kinds of different domains. We talked about just a fundamental aspect, having the two that are kept synchronized. One I haven't discussed, but it's really interesting to me, is modeling what a person is thinking. So in this case, the person's mind, what you're thinking, is going to be represented in the computer. So that sounds weird, right? Well, in a collaboration, actually, we do this, right? We have some expectation of what our partner is doing in our collaborative work, and we do our actions based on our understanding of what's going on in our collaborator's mind. So if we're really going to have cobots work with people, we want to basically represent what's going on. Of course, it's not a perfect representation, but it's at least a partial representation, and we can basically have a much more successful collaboration if we do that. In some cases, there could be very high fidelity. So if we're more interested in so if we're doing additive manufacturing, we might be very much more interested in what's going on at the microstructure of parts and being able to have some sense of what's going on at the microstructure. The three-dimensional parts in a way, the simple parts, so we don't even need to think about that. But what's going on at the microstructure, whether the grains are aligned, is very likely much more critical. Or temporal schedules. Are we in a rush? Do we need to do something faster? And finally, there's no limit here to whether we keep 2 domains in synchrony or whether we keep 5 domains. In some cases, we may want to have 3-dimensional graphics of a machine tool. We may want to have the mental model or the human model of the human's operator's mind of what he's trying to do. We may want to have an idea of what the schedule is for that day. So there might be 3 critical domains that are going on simultaneously, and they all should be synchronized. So digital twins does not rule that out. So with that said, I probably already gone way over my time, but anyway, that's the end of my presentation. And if you have a question or two, that'd be great. And otherwise, as Tom said, we can do that offline.
Yeah, David, thank you very much. This was very interesting. I think it does seem like we're just scratching the surface of how this can really impact the future of manufacturing and just the future of a lot of things with this capability. So for someone who does have questions for you or want to know more about this, where would you suggest that they reach out or visit?
So my email address is Bourne, Bourne, @andrew.cmu.edu.
Great, that sounds great. And anyone can always go through our contact us form on the aimhigherconsortium.org website, and we will be sure to, relay your questions or request for information, and we'll get David involved as needed. So, but again, thanks everyone for participating, and thank you for sharing this with us today. And I look forward to hearing more about this as we continue to evolve.
Thank you.
Thank you. Have a good day, everyone.